Welcome to the Deep Dive, your shortcut to being the most informed person in the room. Today, we're tackling a technology that's, well, it's fundamentally changing everything, artificial
It
intelligence.
really is.
But we're not focusing on, the usual debates about jobs or ethics today. Instead, we're digging into something more fundamental, more physical. The sheer energy challenge AI presents. We're talking about its massive thirst for electricity.
Indeed. AI it's rapidly becoming one of the most consequential technologies out there. Think changes on the scale of electricity itself or the internet.
Right.
And the relationship we're unpacking today, drawing a lot from the International Energy Agency's work, is this complex link between AI and the global energy system.
So our mission here is really twofold. First, we need to grapple with the huge and frankly surging energy demand AI is creating. The IEA calls this energy for AI. And then on the flip side, we explore how AI can actually help the energy sector optimization, efficiency, innovation. That's the AI for energy story.
And that sets up the core paradox, the thing you really need to keep in your head as we go through this.
Yeah.
AI infrastructure, right now, is putting immense strain on electricity grids. It's causing bottlenecks, pushing demand.
While at the same time.
Exactly. While at the same time, it offers these potentially powerful systemic solutions. Solutions that could, theoretically, fix the very problems it's creating and unlock huge efficiencies across the economy. It's this urgent race between consumption and optimization.
Okay, let's start with that consumption side. It's causing a lot of headaches for utilities, for policymakers, pretty much everywhere right now. When we say AI needs energy, we're mainly talking data centers, right? What's the scale here? How fast is it growing?
The scale is already significant. Globally, data centers use around 415 terawatt hours, TWH, in 2024.
415 TWH. How much is that in context?
Well, just that one category, data centers, is about 1.5% of all global electricity consumption. Now, 1.5% might not sound huge on its own.
But the growth.
But the growth rate, yes. It's been averaging a really robust 12% per year over the last 5 years. And that's compound growth. It starts eating into power reserves pretty quickly at that rate.
That 12% is worrying enough, but I think what really makes this a planning nightmare is the uncertainty about the future. The projections seem to vary wildly based on how fast AI actually gets adopted. Can you take us through those scenarios? The range seems huge.
It is. The outlook is really defined by uncertainty. You've got these competing factors. How fast will hardware get more efficient? How quickly will AI models actually be rolled out and used? And crucially, will energy sector bottlenecks, things like grid capacity, physically slow down the build-out?
So what's the sort of middle ground baseline expectation?
Okay, so the IEA has a base case. This is grounded in what the industry expects for server shipments, established efficiency trends. On this path, data center consumption is still set to more than double by 2030, hitting around 945 TWH.
Doubling in 6 years. That's still massive for planning purposes.
Absolutely. Significant enough to really reshape regional power planning.
But the big worry, I guess, is that AI adoption might just blow past those baseline assumptions. It feels different from previous step cycles. That's where the higher scenarios kick in.
Precisely. That's the liftoff case. This scenario assumes AI uptake is stronger, faster, and crucially, that local constraints finding land, getting permits, securing power connections are somehow overcome quickly.
And in that case,
consumption hits over 12,260 TWH by 2030. And if you look out a bit further, to 2035, the gap widens even more. That liftoff case could potentially reach up to 1,720 TWH by 2035.
Wow, 1,720 TWH. That is just a staggering amount of power to plan for, especially when you consider the lower end. What drives that lowest estimate?
Well, the difference between the scenarios by 2035 is really something. You go from maybe 700 TWH on the low end all the way up to that 1,720 TWH. That's like a seven-fold difference. It just highlights how much uncertainty policymakers and investors are dealing with right now.
And that uncertainty must be paralyzing. How does a utility commit billions to new power plants or transmission lines? If the load could be anywhere in that huge range, what defines that lower end, the 700 TWH scenario?
That's essentially the headwinds case. It assumes those grid bottlenecks we talked about, transmission delays, component shortages, plus maybe slower AI uptake due to cost, actually do constrain the build-out physically. In that world, consumption only reaches about 670 TWH by 2030.
Okay.
They also model a high-efficiency case, assuming big breakthroughs in hardware and software savings, which peaks around 800 TWH by 2030. But whatever scenario plays out, the growth is very concentrated geographically. The U.S. sees the biggest absolute jump by far than China and Europe.
So if we look inside these data centers, it's not just more of them, it's that the type of computing is changing, shifting towards specialized AI hardware.
Exactly. The industry has gone through this huge structural shift towards hyperscale data centers. These are the giant facilities run by the big tech players, Amazon, Google, Meta, Microsoft. Their share of total capacity has just exploded. It went from maybe 10% back in 2010 to about 37% today. They're rapidly pushing out the older style, individual company-owned enterprise data centers.
And what makes these hyperscalers different in terms of power?
They're just enormous. A traditional corporate data center might draw 10, maybe 25 megawatts MW. But a modern hyperscale facility, especially one focused on AI, routinely goes over 100 milliW.
100 milliW. Can you put that into perspective?
For sure. A single 100 milliW facility uses about as much electricity in a year as 100,000 average households. And they're getting bigger specifically to house the specialized, power-hungry hardware needed to train and run these increasingly massive AI models.
What's driving this consumption growth within the data centers? Because historically, IT has gotten much more efficient over time.
Efficiency is still improving, definitely, but it's being swamped by three main things. Just huge demand for AI services, a big jump in the number of specialized servers being deployed, and this is critical as slowdown in some of the traditional efficiency gains. Well, with older servers, a lot of energy savings came from reducing idle power, the energy used when the server was just sitting there waiting.
Yeah.
But these high-performance AI servers, they run much closer to full tilt much more often. They're doing these huge parallel computing jobs continuously. So there's just less opportunity for those idle power savings.
This feels like a good moment to bring up something crucial for understanding this whole picture. Efficiency metrics. You hear terms like PUE and WUE thrown around. Why are they so important here?
Absolutely essential for transparency. PUE stands for power usage effectiveness. Basically, it's the ratio of the total energy going into the data center versus the energy actually used by the computers, the IT equipment.
So a perfect score would be?
A perfect PUE is 1.0. Every watt goes to compute. Realistically, a typical value might be, say, 1.5. That means for every watt the computers use, another half watt is needed for cooling, lighting, power distribution, that sort of thing.
Okay, and WEE?
WUE is water usage effectiveness. It measures the water used mainly for cooling relative to the energy consumed by the IT gear. As these data centers get denser and hotter, cooling becomes a massive challenge. Often they shift from air cooling to much more water-intensive methods, which can really strain local water resources.
And the issue is, we don't always get good data on these.
That's the problem. These metrics, PUE and WUE, are fundamental for tracking efficiency and environmental impact, but are often underreported, especially for the newest AI-focused facilities. We need more transparency there.
Okay, so this massive load growth, combined with maybe less than perfect efficiency reporting, seems like it's heading straight for grid problems. You mentioned bottlenecks and delays earlier. Why are so many projects struggling to get connected?
The grid strain is already severe, and it's widespread. Our analysis suggests something like 20% of planned data center projects around the world are at risk of serious delays simply because the grid can't handle them or the connection queues are too long.
What's causing the blockage?
It's a mix of things: regulatory hurdles, financing issues, and just basic physics. Building new high-voltage transmission lines is incredibly slow, especially in advanced economies. We're talking 4 to 8 years, easily, because of permitting battles, land access issues.
And it sounds like even if you get the permits, getting the actual equipment is a problem now, too.
Absolutely. The supply chains for critical power grid components are stretched incredibly thin. You've got demand from AI, but also from electric vehicles, renewable energy buildouts, general electrification.
So everyone wants the same stuff.
Everyone wants the same transformers, the same high-voltage cables. And lead times for those have basically doubled in the last 3 years. It's not just a short-term blip either. Even big stuff, like the gas turbines some regions want to build quickly to back up renewables, the delivery times now stretch out several years. That could push commissioning dates past 2030.
So if the electricity sector can't accelerate its own build-out, this AI demand could force some really tough choices.
Exactly. It could mean choosing between powering new data centers and, say, supporting the electrification of transport, or bringing manufacturing back onshore. There might not be enough grid capacity and equipment for everything at once without a major step up in investment and streamlining. #ManTag3 defining AI and the energy cost of compute.
Okay, we've established AI means big data centers needing lots of power. But let's zoom in a bit on the AI itself. When people hear AI, They often think ChatGPT, text generation, but it's much broader than that, right? And different types presumably have different energy costs.
Definitely. AI systems today fall into a few key functional buckets. First, you have predictive AI. These are models designed to understand complex systems and forecast what might happen next.
Like weather forecasting.
Exactly. Models like GraphCast are now outperforming traditional methods in speed and accuracy for weather prediction. Another huge area is molecular biology systems like AlphaFold, predicting protein structures. That massively accelerates drug discovery by cutting down experimental time.
So that's interpreting complex data. What about interpreting the real physical world?
That brings us to computer vision. This is all about understanding visual information, images, videos. The applications are everywhere. Self-driving cars, identifying obstacles, medical scanners analyzing images for disease, automated quality control in factories.
And then there's AI that actually moves in the real world.
Right, that's physical or embodied AI. Think robots, autonomous vehicles, drone systems that physically interact with their surroundings. The big leap recently is using machine learning to let these systems operate outside controlled environments, like factories. Operating in the messy, unpredictable real world requires constant, fast computation.
Let's talk about the energy costs through the whole AI life cycle, starting right at the beginning, making the hardware.
The manufacturing, especially for the specialized chips in GPUs and AI accelerators, is very energy intensive. Just to give you a sense, making one state-of-the-art 3-nanometer silicon wafer takes about 2.3 megawatt hours of energy.
That sounds like a lot for one wafer.
It is. But you have to put it in context. For a whole high-performance server, the manufacturing energy might add up to over 10 milliwatt-h. However, over its typical 5-year operational lifespan, that same server could easily consume over 80 milliwatt-h.
Ah, okay. So while making it uses a chunk of energy, running it over its lifetime uses far, far more.
Exactly. Operation really dominates the total energy footprint. But then you have the process that gets all the attention that initial huge energy burst needed to train these giant AI models.
Right. Training seems to be where the really big power spikes happen. What do we know about that energy cost?
Well, precise data is hard to come by. Transparency isn't great. But estimates suggest that training all the major large AI models developed globally since around 2020 used something like 1,700 gigawatt hours cumulatively.
Okay. And for a single cutting-edge model?
For the biggest models being trained today, the peak power draw during training can be a massivist. Estimates are around 154 milliW. It's this huge concentrated power demand, but it happens mostly at the start of the model's life. After training, it moves into the inference stage.
Inference, that's when the model is actually being used, like answering a query. How does the energy needed for that change, depending on what you ask it to do?
Inference energy varies a lot. A key factor is the input-output mode. Generating video or complex images, for example, is way more energy intensive than just generating text. It involves manipulating vastly more data points, more pixels.
Makes sense.
Then, obviously, the model size itself matters. A model with, say, 70 billion parameters needs much more computation per query than a smaller 7 billion parameter one.
You mentioned efficiency earlier, and this idea of the AI itself getting smarter about saving energy. How does that work?
Yeah, that's where algorithmic efficiency comes in. A really interesting technique is called mixture of experts, or MOE. Instead of the entire humongous model having to process every single query.
Right.
MOE selectively activates only the relevant expert parts of the model needed for that specific answer. This can save a huge amount of computation, and therefore energy per query, often without hurting performance, sometimes even improving it.
That sounds promising. But you also mentioned models can deliberately use more energy to get a better answer.
Yes, that's called inference time scaling. Basically, the model can be made to think harder about a query, run more internal calculations, cross-check itself to improve the accuracy and reduce the chance of making stuff up, or hallucinating.
So it's a trade-off, more energy for more confidence.
Exactly. It boosts the quality of the answer, but at a significantly higher computational and energy cost for that specific query.
The good news in all this, presumably, is that the hardware itself keeps getting better, more efficient.
Absolutely. Hardware efficiency improvements are the constant counterpressure against this rising demand.
Yeah.
Chip manufacturers are making huge strides. For instance, the latest B200 GPU is estimated to be about 60% more energy efficient, measured in computations per watt, or FLOP watt, than the previous H100 generation.
And the H100 was already much better than the one before it.
Right, the H100 was maybe 80% more efficient than the A100 before that. These big generational leaps are the main reason the consumption forecasts aren't even higher than they are. But again, commercial competition means we often lack transparent, real-world energy use data from these chips in operation, making precise tracking tough.
Okay, so to wrap up this section on AI itself, where does it really shine compared to humans, and where does it still fall short, especially on tasks that might use a lot of energy?
AI is truly superhuman in highly structured tasks with clear rules and massive amounts of data. The classic example is the game of Go. AlphaGo Zero achieved a rating score way beyond any human capability, like 5,185, versus the human best of around 3,890. It's this ability to master vast, complex but defined problem spaces that's now being applied to science, like predicting molecular properties.
But that general flexible intelligence humans have is still missing. What are the main limitations right now?
AI still struggles with true novelty and generalization. Things like metacognition, knowing what you know and don't know, or applying logic learned in one area to a completely new situation, or understanding subtle social cues, those are still major challenges. That's partly why AI can hallucinate confidently, state things that are just wrong. It lacks that self-awareness.
And in the physical world, you mentioned self-driving cars earlier. The learning process seems very different.
It really highlights the gap. To get a self-driving system to level 4 autonomy, which is high automation but still geographically limited, often takes processing data from something like 20 million miles of real-world driving. Compare that to a human driver. We reach level 5 full autonomy anywhere after maybe 70 hours of practice. That massive difference shows machines still need vastly more data to achieve the kind of flexible, abstracted learning humans do so naturally. Plus, you have practical hardware limits the precision of sensors, robot joints that also slow down progress in physical AI. Okay, so now let's flip the coin. We've talked a lot about the energy demand of AI. Now let's look at its potential to help. We're leaning here on the IEA's widespread adoption case, or WOC.
Right, and it's important to understand what that means methodology-wise.
Yes. The WOC isn't predicting the future. It's assessing the potential impact if known. Existing AI applications were widely adopted across different sectors by 2035. So it's about potential, but achieving it depends on policy, investment, overcoming adoption barriers. It's not guaranteed.
Got it. So starting at the source energy supply, how can AI help optimize things like finding oil and gas or critical minerals, even in industries that maybe haven't always been quick to adopt new tech?
Well, the oil and gas sector was actually an early adopter, mainly because reducing uncertainty in exploration is incredibly valuable. AI is now used routinely to analyze seismic data, making resource evaluation much more accurate, cutting down the guesswork before drilling.
And the impact.
Widespread use could potentially cut the cost of developing new deepwater oil fields by up to 10%. That makes extraction more precise, potentially more economical.
And beyond cost, what about emissions? Methane leaks are a huge issue in oil and gas operations.
Methane is a prime target for AI. Imagine replacing infrequent manual leak checks with continuous AI-powered monitoring systems. If you did that globally at sites currently only checked quarterly or annually, you could prevent nearly 2 million tons of methane emissions.
Which is equivalent to how much CO2?
That's about 60 million tons of CO2 equivalent. And here's the kicker. The estimated cost of deploying that AI monitoring, around 1.66 per million BTU, is actually cheaper than the cost of those traditional labor-intensive quarterly checks. So it's cheaper and better for the climate.
A win-win. Okay, what about the minerals needed for the energy transition itself and for AI hardware? Copper, lithium, etc.
Yeah, AI is becoming really important there too for managing resources and speeding up discovery. There's a company, Cobalt Metals, using machine learning to analyze historical geological data drilling results, seismic surveys to pinpoint promising areas for minerals like copper.
Like they did in Zambia.
Exactly, with the Mingumba Copper Project. Their AI guided the exploration, making it much more targeted, saving time, and reducing the need for tons of expensive speculative drilling. It helps bring these essential minerals online faster.
Okay, moving to the electricity sector itself, the very system AI is straining. How can AI turn around and help fix grid problems? This seems like a key area.
It really is. The grid is getting way more complex with all the variable renewables, wind, solar, and AI thrives on that kind of complexity. It's already making a big difference in forecasting renewable energy output. Better forecasts mean less wasted energy, less curtailment, and help grid operators manage supply and demand. DeepMind, for instance, developed a system that improved the financial value of wind power by about 20%, just by predicting output more accurately, allowing operators to sell the power when prices were best.
And what about reliability, keeping the lights on when things go wrong?
AI-based fault detection is another big one. These systems can analyze grid data to pinpoint the exact location of a fault, a downed wire, a failing transformer much faster than traditional methods. That can cut outage times by 30% to 50%, which is huge for customers.
Wow.
But maybe the biggest potential impact comes from unlocking capacity on the lines we already have, using a technology called dynamic line rating, or DLR.
DLR. Okay, explain that. How does it unlock capacity on existing wires?
So traditionally, the maximum amount of power a transmission line is allowed to carry is set very conservatively, based on worst-case weather conditions like a really hot day with no wind to prevent the line overheating and sagging too much.
Right.
DLR uses sensors and AI models to look at the actual real-time conditions, wind speed, air temperature, solar radiation, and dynamically calculate how much power the line can safely carry right now. Often it's significantly more than the static conservative limit.
So it's like finding hidden bandwidth on the grid.
Exactly. You're squeezing out spare capacity that was just being left unused. And the amount can be huge. The IEA estimates that widespread DLR powered by AI could unlock somewhere between 115 and 175 gigawatts of additional transmission capacity globally.
115 to 175 GW, just from existing lines.
Just from existing lines. Now, think back to the AI demand problem we started with. That range of 115 175 GW is actually more than the total projected increase in global data center power demand by 2030 in the base case scenario.
That is stunning. So AI could potentially unlock enough existing grid capacity to handle its own projected growth, and maybe even more.
Potentially, yes. It perfectly illustrates that paradox we talked about. AI creates the demand, but AI applications could provide the capacity solution. It's not guaranteed. DLR deployment needs to accelerate, but the potential is there.
Amazing. What about managing the grid assets themselves? Poles, wires, transformers?
Utilities are increasingly using AI for predictive maintenance. Around 70% told the IEA they're using it for asset management. Things like using drones with image recognition AI to spot vegetation growing too close to lines, or identifying subtle signs of wear on equipment before it fails.
And that saves money.
Big money. If AI-driven maintenance can extend the average lifespan of grid assets by just 2 years, that could defer something like $300 billion in cumulative grid investment globally by 2035. That's capital freed up for other priorities just by being smarter about maintenance.
Okay, finally, let's look downstream at the big energy users, transport and buildings. These are tough sectors to decarbonize. What can AI do there?
The potential savings are massive. In transport alone, the widespread adoption case suggests AI could save energy equivalent to what 120 million cars use annually. That's over 4.5 exajoules EJ by 2035.
Where do those savings come from mainly?
A lot comes from road freight. Optimizing delivery routes, reducing time stuck in traffic, cutting down on engine idling AI can man off that complex logistic network far better than traditional methods. That alone could save over 3 EJ by 2035.
Even aviation, which is already obsessed with fuel efficiency, can benefit. You mentioned savings of 5–12% per flight. How?
It's about hyper-optimization using real-time data. AI systems can constantly analyze atmospheric conditions, winds, temperature, air density along the flight path, and fine-tune the route in ways human pilots or dispatchers just can't. That small percentage saving per flight adds up across the global fleet.
And it can help with contrails, too. Those white streaks planes leave.
Yes, and that's important because contrails actually have a significant warming effect, maybe even more than the CO2 from burning the fuel. AI can predict where atmospheric conditions are ripe for contrail formation and suggest tiny route adjustments to avoid those areas. Estimates suggest this could cut contrail formation by over 50% with only a very small fuel penalty, less than 0.5% increase across the fleet.
But there's a catch with transport efficiency, isn't there? The rebound effect.
Absolutely. This is a huge caveat. If AI makes driving, especially autonomous driving, cheaper or more convenient, it could encourage more driving. People might ditch public transport or commute longer distances. That induced demand could eat into or even wipe out the efficiency gains. Policy is crucial to manage that.
Okay. And buildings, they're often described as fragmented, making it hard to implement changes.
Buildings are tricky due to fragmentation and often slow digitalization. But the potential is still huge. If known AI-driven energy management techniques were scaled up globally, savings could reach around 300 TWh by 2035.
How much is 300 TWh?
That's roughly the total annual electricity generation of Australia and New Zealand combined. So significant savings.
And buildings can also help the grid.
Yes, by providing flexibility. AI-enabled building management systems can react intelligently to grid signals, like changing electricity prices or grid stress events. They can coordinate things like HVAC systems, water heaters, EV chargers, shifting their demand at times when power is cheaper or cleaner. This demand flexibility from buildings could add over 400 gigawatt of capacity to the grid globally. That's like 10% of peak demand without building new power plants. Hashtag tag V, AI's role in accelerating energy innovation.
So we've seen AI optimizing what we already have, but what about its role in speeding up the next generation of energy tech? Innovation in energy has historically been quite slow, right?
Painfully slow, often. That's the big challenge. If you look at really foundational technologies like solar panels or lithium-ion batteries, the average time from the first lab invention to the first commercial product was over 30 years.
30 years.
And then often another 20 years after that to reach widespread market adoption. AI's big promise in the R&D space is to drastically compress those timelines, especially that initial risky proving phase, getting from a basic concept to something that actually works reliably, say technology readiness levels 1 to 6.
Where does AI make the biggest difference in the lab? What kinds of problems is it best suited for?
It really shines where the number of possibilities is just astronomically large, where human intuition or trial and error would take forever. Think designing new catalysts for chemical reactions, discovering completely novel battery chemistries with better performance and safety, or screening millions of potential materials to find ones that capture CO2 efficiently.
Like finding a needle in a haystack, but the haystack is galaxy-sized.
Exactly. One estimate suggests we've only experimentally made something like 0.01% of all theoretically possible materials for next-generation solar cells. AI provides a way to explore that vast, uncharted territory much more systematically.
And it's not just designing things computationally, it's automating the lab work itself, this idea of self-driving laboratories.
Yes, that's a really exciting development. These are automated systems where AI directs the entire research cycle. The AI proposes a new material or experiment, robots synthesize or run it, automated instruments analyze the results, and then the AI uses that new data to decide the next experiment.
Like the A lab at Lawrence Berkeley.
That's a great example. They've basically automated the whole loop. It cuts the time for each cycle down from weeks or months for a human researcher to potentially just days. It's about massively accelerating that learning and refinement process.
Okay, let's look at specific areas. Batteries are obviously crucial for renewables and EVs. How is AI helping there?
Battery R&D is incredibly complex. You're juggling materials, science, electrochemistry, manufacturing tolerances, predicting how performance degrades over thousands of cycles. It's a huge multivariable optimization problem.
Too complex for humans alone.
Pretty much impossible for humans to explore exhaustively. AI-driven materials discovery combined with that automated high-throughput testing could potentially slash the time to identify promising new battery chemistries by maybe tenfold down to months instead of years. And AI is also critical on the factory floor, analyzing billions of data points from production lines in real time to catch tiny defects that could affect battery life or safety later on.
What about synthetic fuels? Things needed for planes or ships that are hard to electrify.
Right. Fuels made via processes like Fischer-Tropsch synthesis. These reactions depend heavily on catalysts, and finding better catalysts is key. AI can screen potential catalyst candidates thousands of times faster than traditional experimental methods. It drastically speeds up that initial discovery or proving phase.
But scaling up production is still a challenge.
Scaling up remains a major engineering hurdle, yes.
Yeah.
AI helps find the recipe faster, but actually building the industrial-scale kitchen is still hard work.
Carbon capture CCUS. That often suffers from a high energy penalty, making it expensive. Can AI help find more efficient capture methods?
That's the goal. Current methods often use way more energy than theoretically needed. AI is being used to design new materials like specific metal organic frameworks, or MOFs, and specialized solvents that can grab CO2 much more selectively and efficiently, using less energy for the capture and release cycle.
How much faster?
Using AI for the computational screening and design could potentially cut the time to market for these better capture materials by around 30%.
But you mentioned a data problem here earlier.
Yes, that's a key limitation right now. A lot of the AI training data comes from lab-scale experiments or computer simulations. It often doesn't reflect the harsh real-world conditions inside an industrial plant, high temperatures, impurities in the gas stream. So the AI might predict great performance in the lab, but it doesn't translate perfectly to industrial scale. You still need that expensive, time-consuming physical pilot testing.
Okay, one last sector. Cement. Huge emissions, but historically not much R&D spending.
Cement is a really tough nut to crack. Massive emissions, but the industry has traditionally invested very little in fundamental R&D compared to its size. AI can help, for example, by creating predictive models to optimize concrete mixes that use less clinker, the most carbon-intensive ingredient.
But the data is sparse.
Extremely sparse. The main global dataset used to train models for predicting concrete strength, believe it or not, only has about 1,000 entries, and the data is from 1998. Plus, cement plants last a long time, over 25 years typically, so replacing the existing infrastructure is slow. Even with AI helping, the estimated time to market reduction for breakthrough low-carbon cement is maybe only around 20%. It's a harder, slower transition.
Okay, we've covered the demand AI creates and the potential solutions it offers. Let's zoom out now to the bigger picture. Policy, investment, and ultimately, the climate impact. The financial markets have certainly reacted strongly to AI.
Strongly is an understatement. It's been explosive. Since ChatGPT launched in late 2022, the S&P 500 index gained about $16 trillion in market value. And get this, $12 trillion of that $16 trillion gain came from AI-related companies.
Wow, $12 trillion out of $16 trillion. That's incredible concentration.
It reflects massive market expectations about future profits, and that translates directly into spending on infrastructure right now.
And that spending is huge.
Astronomical. The big tech firms, Alphabet, Amazon, Meta, Microsoft, are planning to spend around $300 billion on AI-related capital projects just in 2025.
$300 billion in 1 year. How does that compare?
Well, $300 billion is over 20% more than the entire power sector investment across the whole United States in a typical year. Looking ahead, the base case projects $4.2 trillion in cumulative data center investment globally between 2025 and 2030. And just connecting those data centers will require an extra $480 billion in power sector investment worldwide.
So unprecedented AI investment is colliding with stressed energy supply chains.
Exactly. That convergence of demand is causing real shortages. We already mentioned lead times for things like transformers have doubled because everyone needs them, AI, EVs, renewables. And the cost of key materials, like the special electrical steel for efficient transformers, has jumped 60% in 4 years. That adds cost and delay to building out the grid.
And the AI hardware itself depends on specific minerals, adding another layer of risk, geopolitical risk.
Definitely. AI chips and servers need silicon, copper, rare earths, gallium, and the refining for many of these is highly concentrated geographically. China, for example, accounts for a quarter of the global trade in transformers, and they've already put export restrictions on key semiconductor minerals like gallium and germanium. So mineral supply chain security is a real vulnerability for scaling up both AI and the grid needed to power it.
This investment scale and the supply chain issues bring us to the digital divide. What about emerging markets and developing economies, EMDEs?
It's a major challenge. Many EMDEs struggle with basic power reliability. Some places have over 700 hours of power outages per year. That makes building and running a data center locally incredibly difficult and risky. Many businesses end up hosting their data overseas, which isn't ideal for local digital growth.
But people in those countries are using AI.
Very much so. Generative AI adoption is surprisingly global. In countries like Brazil, India, Indonesia, over 50% of the online population report using generative AI weekly. That's actually a higher rate than in some advanced economies among internet users.
So, high demand for the service, but unreliable infrastructure to host it locally. How can EMDEs attract data center investment despite those power challenges?
One interesting mechanism is data centers acting as demand anchors for new renewable energy projects. The big tech companies sign these long-term contracts called corporate power purchase agreements, or PPAs, guaranteeing they'll buy the power from a specific new solar or wind farm.
How does that help?
In places where the local utility might have a weak credit rating, having a PPA from a major creditworthy tech company makes the renewable project much more bankable. It improves the project's creditworthiness significantly. We've seen estimates of like a 6 to 12 notch improvement in credit rating. That unlocks private finance that otherwise might not have been available for clean energy in that region.
Fascinating. Okay, the bottom line question. Emissions. Taking everything into account, is AI helping or hurting the climate transition?
It's a tool, a powerful one, but definitely not a silver bullet. Under the base case scenario, data center emissions themselves are projected to peak around 320 million tons of CO2 by 2030, then maybe decline slightly to 300 million tons by 2035.
Which is how much of the total?
It stays below 1.5% of total energy sector emissions, so growing fast, but still a relatively small slice of the overall pie.
But the potential savings from using AI.
That's the hopeful side. If those existing AI applications we discussed in transport, buildings, grid optimization are widely adopted, the potential emissions reductions could reach 1.4 gigatons of CO2 by 2035.
1.4 gigatons.
Yeah.
How does that compare to the data center emissions?
It's potentially up to 5 times larger. So the potential benefit from using AI across the economy could far outweigh the direct emissions cost of running the AI itself.
And this is a big, that potential isn't automatic. Policy matters, and that rebound effect is still a risk.
Absolutely critical points. Achieving those savings depends entirely on proactive policies to overcome adoption hurdles. And yes, the rebound effect is always lurking. If AI makes, say, extracting oil cheaper, does that lead to more oil consumption, potentially offsetting the gains? If autonomous cars make driving easier, do people abandon trains and buses? AI doesn't magically solve these behavioral and market dynamics. We still need strong policies to ensure efficiency gains translate into actual decarbonization, not just more overall activity. Hashtag tag J7, outro and final provocative thought.
Well, this has been a really deep dive into a fundamental tension shaping our future. We've seen this dual reality, the frankly staggering energy demand AI is placing on our grids, causing real bottlenecks and supply chain stress. And at the same time, this enormous potential AI holds for optimizing everything, unlocking huge amounts of grid capacity with DLR, slashing energy use in transport and buildings.
The immediate problem, though, really comes back to data, doesn't it? That lack of transparency. We talked about that huge 7-fold difference in the projections for future data center energy demand.
Yeah.
How can anyone plan effectively with that much uncertainty?
Right.
We desperately need better standardized reporting, especially on those core metrics: power usage effectiveness, PUE, and water usage effectiveness, WE, consistently across the board.
Which kind of brings us full circle and to a final thought. Today, we mostly talked about AI as a tool that humans use to innovate faster, finding better battery materials, designing catalysts. But what if AI becomes more than just a tool?
What if AI itself becomes the engine of innovation?
Exactly. If AI truly excels at finding solutions that humans can't even conceive of, optimizing systems far beyond our intuition, what does that look like in the long run?
Well, think about some of those huge, seemingly intractable energy waste problems we have. You mentioned earlier, something like 45 exajoules of energy is wasted globally, just moving empty vehicle weight around instead of people. That's almost double the final energy use of the entire African continent.
Just wasted.
Just wasted. Could a future, maybe self-improving AI, design systems to eliminate that? Could it design a transportation network with near zero congestion? Or an electrical grid with practically zero losses? Or buildings that require no external energy input at all?
That's the really radical long-term vision, isn't it? Not just AI as a tool for efficiency, but AI as a self-sustaining engine, designing fundamentally new systems that are inherently efficient, inherently sustainable.
Perhaps. An AI that could not only help fix the energy problems it creates, but ultimately design a cleaner, smarter system from the ground up. That's the horizon.
A fascinating and slightly daunting thought to end on. Thank you for joining us for this deep dive.